Okay, we're going to continue with our discussion of work energy methods, and in particular here we're going to talk about conservative forces and potential energy. Um, Once we understand this, we can do lots of relevant problems using work energy methods. This is from section 4-2 in the text. So we want to describe what we mean by potential energy and conservative forces, and then we'll do some examples about how to apply these to engineering problems. So we've talked about work. We've derived this formula for the work done, U1, 2, and going from position 1 to position 2 under some force F, and it's just the integral over the path of F dot dr. And for many cases, for many types of forces, this work done is independent of the path. So all it matters is where you start and where you finish. And for problems uh, involving forces like that, then all you need to know is kinetic energy starting and finishing, potential energy starting and finishing, and that lets you solve the problem. And so we'll look at how that works. So let's look at gravity, for example. Gravity is a constant force, and as we saw before, the under a constant force, the work done on a particle is just the force times dotted with the vector from position 1 to position 2. And so, since gravity is a constant force, then we can just write that, for example, the work done in going from position 1 to 2 in something that's moving vertically is just minus mg, where g is a gravitational constant, times the difference in the heights, right? So if we move this gondola, for example, from position 1 to position 2, the potential energy change only depends on the change in height. Doesn't matter how far you move horizontally, doesn't matter on what happens as you go along the path. It just the height change from position 1 to position 2. Okay, path independent. Anytime we have a central force, uh, the same sort of thing applies. So, for example, if there's a force on a particle that always acts through point O, then point O is the center of the force, right? So no matter where we are, the force on the particle points back to point O. That's referred to as a central force. If we think of a satellite traveling around a planet, then the gravitational force between the satellite and the planet always passes through the center of the planet. So that would apply here. So we can derive the work done. So the central force is just some magnitude Fc, which depends only on r, the distance from the center to the position of the particle, and then it acts along this unit vector, radial unit vector. So the work done in going from point 1 to point 2 from a central force is just the integral of f dot dr. We can write dr as v dt, so it's the integral from t1 to t2 of f dot v dt. Okay, so it's the integral of the central force we write as fc, a magnitude, times this unit radial vector. And then the velocity has a radial component and a azimuthal component. And it turns out then that the central force is perpendicular to this azimuthal component, so that part of the velocity is not affected. So it's fcr dot dt, which we can write as fcdr, right? So the work done by the central force is just the integral from r1 to r2 of fc of r dr. So all that matters is the change in distance from the center of this force, and it doesn't matter how far around you travel at all. So that's effectively the same as the gravity we talked about before. A spring is similar. Okay, so suppose we have a spring, attached to point O and connected to a particle. as we move the particle out from point 1 to point 2, we have to stretch the spring. It takes work to do that. And so it acts like a central force because the force on the particle is always pointing back to the anchor point for the spring. So it acts like a central force and will work similarly. Okay, so we say the central force in this case is just the spring constant K times the amount it's been stretched. So if L naught is the length of the spring when there's no force applied, then R minus L naught tells you how much you've stretched the spring, and that times the spring constant tells you how much force you had to apply to do that. So that's our force. We put that into this central force formula we just derived. So the potential, uh, the work done in moving from point 1 to point 2 from the central force is just the integral from R1 to R2 of that Fc of R dr. And so for Fc, we put in minus K times R minus L naught, and then we do this integral, and we find the work done is minus 1/2 the spring constant times the square of the distance of the change, the stretch in the spring, delta 2 squared minus the stretch initially, right? And the stretch is just R minus L naught, the change from this force-free length to the length either at position 1 or position 2. So this is a formula we'll use quite a bit as we do these work energy problems. So the work done by a spring is 1/2 K times the difference in the squares of the stretches from one position to another. We can look at gravity, right? So we have a body A, think of this as maybe the planet Earth, and body B, this could be the moon or a satellite. And there's a central force between the two. It's given by this universal gravitational constant, capital G, times the product of the masses of the two bodies, divided by the square of the distance. And the direction is given by this radial um, unit vector. Okay, so the work done in going from position 1 to position 2 along this path, for example, is integral of R1 to R2 of GMM over R squared dr. G times M, is a constant. GMM is a constant. We can pull those out. So it's the integral of dr over R squared. So we get the work done by this gravitational force is minus this universal gravitational constant times the product of the masses times the difference in the inverse of the distance between the two bodies initially and finally, right? So 1 over R1 is 1 over the initial separation distance, and then we subtract off 1 over R2, where R2 is the final separation distance. All right, so how does this play into our work energy approach? So we've looked at several examples of conservative forces and the potential energy or the work done by those forces as a body moves in space. And so the question is, how do we apply this to our work energy problem? So we're going to introduce a thing called the potential energy, all right? So we saw that the work done is F dot dr. We can write F dot dr as just dV, where V is some potential energy function. And the integral over the path of minus dV is just minus V2 minus V1. So the potential at V2 minus the potential at V1, right? So all we have to do for all our different central forces is write down the appropriate potential. And then we see that the work done is just the difference in potential energy going from position 2 to position 1, or from 1 to 2 actually. Okay, so there's a scalar function V called potential energy, and it's different depending on whether we're talking about a spring or gravity or whatever. So we define our potential for a certain force, and then the work done in going from position 1 to position 2 is just minus the difference in the potential energies. And so we can conserve energy with an equation like this. So T1 is the kinetic energy of particle 1 of the particle at point 1, and V is the potential energy of the particle at point 1, and then T is a kinetic energy at point 2, V is a potential energy at point 2, and as long as the force is conservative, that is no energy is lost due to the force, then we can write down this expression and say that the total energy is conserved, right? So T1 plus V1 is potential plus kinetic energy initially. T2 plus V2 is potential plus kinetic energy finally. And if it's conserved, then those two have to be equal. So what will usually happen is from point 1 to point 2, T1 will change. Let's say it's reduced, then V will increase to balance it, right? So we're exchanging potential energy for kinetic energy. All right, so we need to know the potential energy for these different forces. Turns out for a constant gravitational force, the potential energy is just mg times y, where y is the vertical distance traveled from some datum point. For a spring force, we saw the potential energy is 1/2 k times delta squared, where delta is the amount of stretch in the spring. And for the universal law of gravitation, then the potential is minus g times the product of the masses over the distance between the two bodies. Okay, now sometimes there are non-conservative forces. One we'll see commonly is friction. Whenever you have friction, it dissipates the energy of the system. That's not a conservative force. So in order to include non-conservative forces, then we have to write our conservation like this. The initial kinetic energy plus the work done going from the initial position to the final position by conservative forces, plus the work done and going from point 1 to point 2 by non-conservative forces equals the final kinetic energy. All right. Now this part, the work done by conservative forces can be represented by these potential energies. So T1 plus V1 plus the work done by non-conservative forces is T2 plus V2. So let's look at a couple of examples. Suppose we have a wrecking ball. We just have a ball attached to the top of this crane by a rope or a wire or cable, and we have it at some angle beta relative to the vertical, and we let go, and it swings down here and crashes into this wall at some angle gamma from the vertical. And so the question is, what's the velocity of the ball when it whacks this wall? So what's happening is there's a slight change in potential energy, right? At this point, you're a little bit higher than at this point. And so the potential energy has changed, and therefore the kinetic energy will change. So we'll say we have a zero initial kinetic energy here. Then in getting to here, we have a change in potential, and that change in potential is reflected in an increase in the kinetic energy, and that lets us calculate the velocity. All right, so we model the wrecking ball as a particle. There's a tension from the cable on the ball, but the tension always acts perpendicular to the motion. So it does no work. And so we don't have to worry about the tension in that cable as we do this problem. Okay, so that's a big benefit. So this is a conservative problem. The only potential energy we have to worry about is due to gravity, and we can just work this out. So T1 plus V1 equals T2 plus V2. There's no non-conservative forces here, no friction or anything like that. T1 is the initial kinetic energy. It's 1/2 mv1 squared. And as we'll say later, V1 is 0. So the initial kinetic energy is 0. We let this go from rest. And T2 is 1/2 mv2 squared. And V2 is the speed of the ball when it hits this wall. So then we need the potential energy. We define we can define zero potential anywhere we want to because all we're worried about is changes in potential energy. So we assign zero potential to be here. We could do it here too. That would probably be a little cleaner, but we'll do it here. Okay, so zero potential is here. So the the potential energy at point one is minus mg times L cosine beta. L is the length of the cable, and L cosine beta then is the height from the datum to here. That's the potential. And the potential at point two is MGL cosine gamma. So it's just a different angle. It's the distance, vertical distance down to this point. And the difference between the two will end up being the change in potential energy. So we just substitute in minus MGL cosine beta, that's the initial potential, equals the final kinetic energy plus the final potential energy. And then we know this, so we move this over and then solve for V2, and we get the square root of 2GL times the difference in the cosines of these angles, and we get 13 feet per second. So that's the velocity of the speed of the ball when it hits that wall. Okay, and dimensions are all correct, and everything looks good. All right, let's look at another example. Suppose we have a box sitting on the top of this RV, and we have a little ramp, and we're just going to slide the crate down the ramp. Um, it's traveling 19 feet along the ramp, and it starts at a height of 11 feet, so you can figure out the angle of this. And so the question is, how fast is the crate traveling when it hits the bottom? And we'll do it two ways. One, with no friction between the crate and the ramp. That way, all the forces are conservative, and we can solve it that way. And then in the second part, we'll include the friction with the ramp, so there is a non-conservative force here. Okay, we'll model the crate as a particle. Notice there's a normal force on the crate, acts perpendicular to the ramp, but the motion is parallel to the ramp. So the normal force dotted with the the velocity vector is 0, and so that normal force does no work. So we don't have to worry about it. If you calculate the angle, notice that the sine of the angle is 35 degrees. I mean, the angle itself is 35 degrees. All right, so let's look at our balance. In general, the balance is this. The initial kinetic energy plus the initial potential is, plus the work done by non-conservative forces is the final kinetic plus the final potential energy. In part A, this term is 0. In part B, this term comes from the friction because that's a non-conservative force. The initial kinetic energy is here. We'll assume that's 0 later. The final kinetic energy is here. That's what we're trying to calculate, or really V2 is what we're trying to calculate. Notice the normal force is just mg cosine theta, where theta is this angle here. All right. So the datum we'll assume is the ground. So V1 is mg times the height, the vertical height to the initial height of the crate. And then V2 is 0, right? When it gets here, there's no potential energy when it gets to the bottom. When we do part B, then the work done by the friction is the friction force times the distance traveled. The force is mu n, and n is mg cosine theta, right? It's the component of gravity perpendicular to the ramp, and the distance traveled is the length of the ramp, right? And so that's the work done by the friction on the crate, right? And again, we assume we start from rest and then let the box go. So for part A, we ignore the friction term here, and we just get the change in potential energy, mgh, is equal to the change in kinetic energy, 1/2 mv2 squared. And we can solve for v2, and we get 26.6 feet per second. So that's the velocity of the crate when it gets to the bottom. For case B, then we leave in the friction, and we just solve for v2, leaving in this term. We know everything in it. It's just a straightforward calculation, and we get 19.7 feet per second. So it's quite a bit slower because we're losing energy due to friction in the system as the crate falls to the bottom, and therefore the velocity is slower when it gets to the bottom. All right. So again, the answers are correct, and the effect of the friction is appropriately handled, and so this looks pretty good. All right. So those are a couple of examples of how to handle conservative forces in problems like